Okay, so welcome to Math 140 Calc 2. This is lecture 29 and April 27th. Okay, so what I want to do today is, again, review of some of the material we've been seeing, focusing on some applications, a little bit of new material, talking a little bit about radial integration. This is a topic that's not really done too much. When I search the topics in the class online, this is one of the ones where it's harder than others to find things on the web to just cull for the lecture. I want to talk a little bit about multivariable calculus because this should be the time of semester where you're thinking about what you might want to take next semester, next year, and it might not be a bad idea to have a sense of, so what can you do after taking Calc 2? Well, to some extent, the numbering really suggests what you might want to do after Calc 2. Calc 3 is a very natural next course to take. All right. We will also be doing a little prep work because we are going to be going to the library on Friday to talk about the quest to understand the cosmos. And trying to understand the orbits of the planets was one of the great impetuses for the development of a lot of mathematics and physics. And so I don't want to do too much right now, but I want to do at least a little bit in preparation. And it's a nice application. It's an interesting way to talk a little bit about the Taylor series stuff that we've been doing. So here we go. So these are some notes that I made many, many years ago when I was teaching Math 150. And it's basically trying to discuss how could we model orbits of planets. So how many of you have had to read the ancient Greek philosophers? Yeah, I mean, this is a liberal arts college, at least some hints for. And so they believed the circle was perfect motion. They tried to understand everything in terms of circular behavior. So if you try to look at the orbits of the planets, the question was, well, maybe they orbit the Earth in circles, or maybe if not that, maybe they orbit the sun in circles. But if you start looking at the observations, you will see very quickly that it can't be circular motion. So then the question is, what if you had a circle, and then on that circle, you had a circle with a smaller radius? And you have something turning on that circle, while that big circle is turning as well. What can you do with this? You can get obviously more shapes. And if that isn't enough, what could you do after you have a circle on a circle? A circle on a circle on a circle, right? This is, the Earth is held up by a tortoise, which is on a bigger tortoise, which is on a bigger tortoise, something like that going on in infinitum. And so, I just made some quick animations to try to show you what things would look like. So these are parametric plots. So I'm giving you positional coordinates x of t, y of t as cosine t, sine of t. And so this is just plotting a circle, t goes from 0 to 2 pi. I can turn this a little bit into a movie. And so what I can do is I will let it play. And you can see, as time increases, it's just moving in a nice circular motion. You should just go all the way around and then should reset. All right, so this is just x of t is cosine t, y of t is just sine of t, and just goes on and on and on. Okay. You could do three-dimensional curves, and so this is x of t, y of t into the z coordinate. I'm just making it t over 20. And so this will give us a nice helical structure. That's what I have this play. You can see as time passes, it's going higher and higher. If you were to look straight down on it, you would see a circular motion. But from this angle, we can see that it is spiraling upward. Now let's try to do some more interesting behaviors. So what I'm going to do now is I'm going to plot always cosine t, sine of t. That's always going to be a circle. Then the next one, the x coordinate is cosine t plus r cosine ts, and the y coordinate is sine of t plus r sine ts. So it starts off with that circle. And then, if r is not 0, I have a circle around that circle. So for example, here are different choices. So here's what's going on, and you'll see the two different ones. Now I've chosen, if you look carefully, my s to be 1.5, which is a rational number of 3/2. If it's perfectly rational, what's going to happen is every time t increases by a certain amount, it's going to essentially reset and you're going to get periodic behavior. If I take S to be 0, what do you think would happen if S is 0? What would this just become? So if S is 0, what does cosine of TS become? It becomes 1. And what does sine T of S become? 0. So this would just become a circle with a larger radius. So as I set S small and small and smaller, you can see it's converging to just going on a circle of a larger radius. Or just shifting things off a little bit. So this is always going to be the exponential. It's just going to be shifting the whole circle 5 units to the right side. And then over here, you're playing the same games and just seeing what happens for different choices. See now I'm getting this nice kind of retrograde motion where it's moving and it looks like it's coming back. And again, as I adjust the different sizes, so here R is the radius. As I make the radius small and small and smaller, it seems to be converging. It's R is going all the way down to 0.2. So I make R go all the way down to 0. You can see it goes back just to the initial thing. The reason it's red is because I originally told it I don't want R to be smaller than 0.2. So that's why I'm just saying, I've chosen something smaller than the range I promised I was going to look at. If I make it 0.01, oh, that's 1, not 0.01. Oh, that's pretty. So here's 0.01. And you can see if you have really good vision, and I brought my glasses because I needed to, that's not quite on the circle. If I move it up just a little bit, 0.05, you can begin to see now the fluctuations. This might look almost something like you've seen in quantum mechanics. Some of these waves with the nice integer multiples coming around. And so as I increase R more and more, I'm going to start to get more interesting behavior as this goes on. And now, eventually it gets to the point where R becomes so large, it's actually going to now be hitting the center. This would be very strange orbital dynamics. But this behavior, which I think is much prettier than a lot of things I've seen in museums, is just from circles on circles on circles. So just as we looked at Taylor series to try to explain a complicated function in terms of simpler ones, I want you to get this as a general theme from the class. If you have a very complicated natural phenomenon that you're trying to understand, try to break it into simpler things. And if I understand how circles go together, maybe I can somehow combine circular motion on circular motion on circular motion to get something that's going to describe a more general shape. And the question becomes, what's the most general shape I can describe with circles on circles on circles? And maybe I allow myself to travel at different speeds on the different circles and whatnot. All right, so this is all I want to do, just prepare a little bit for lecture on Friday. Okay. Any questions on stuff like this? Okay. Let's go back to oops. Back to the main lecture. What I want to do is I want to talk a little bit about ways to find areas of curves. So one of the things I've mentioned is after you take multivariable calculus, after you take Calc 2, Calc 3, or multivariable calculus is a natural next step. Some places do linear algebra next. And some places actually do a unified year-long linear algebra multivariable calculus, because that way you don't have to choose between the two. And there's advantages and disadvantages to both. If I had to sum up the main idea of linear algebra in one sentence, I would be upset because it has a lot of beautiful ideas and whatnot, and I hate picking and choosing. But if I had to choose, I would say linear algebra is all about finding the right coordinate system for what you're doing. How many people know why I am willing to concede that part of New York does something better than Boston? What part of New York do I have to give it credit for? The streets where? Which part of New York is the grid?
New York City.
Which part of New York City? New York City is very vast. Manhattan. Manhattan is a beautiful grid system. We have the north-south and you have the east-west. When you look at Boston, where you can have ComAv and Beacon switching as to which one is above the other, it's a nightmare to get around in Boston. I have to give credit for that. when you have a natural grid like this, if you don't align your coordinate axes with the grid, you're an idiot. This is the natural system to evaluate. We talked about, I think earlier, if I give you an ellipse like this, aligned with the coordinate axes, its equation x over a squared plus y over b squared equals 1. But if I give you an ellipse like this, where it's not oriented along the coordinate axis, now it's much harder to write down what's the equation of the ellipse. And this is where you're going to have the cross xy terms. So you should have seen conic sections when you did algebra 2. It's almost completely forgotten by the time you get to college. But you should be aware that conic sections exist and that there are formulas for stuff like this. And if they're aligned with the coordinate axes, it's not so bad. Well, if it's not aligned with the coordinate axes, what this is basically saying is we did a stupid thing by choosing these to be our coordinate axes. Why don't we choose a better set of coordinate axes? And so if we choose these to be the coordinate axes, say u and v, now all of a sudden we can easily write down what's going on in terms of u and v space. And so we would have u over a squared plus v over b squared equals 1. And now we would write u as a function of x and y and v as a function of x and y. And then we would feed that into the above. And so if we can figure out how you transform from one coordinate system to the other, solve the problem in the easiest system, and then invert backwards. So this is one of the key ideas in linear algebra, is whatever problem you're given, find what is the natural system to study it. So there's a lot of really interesting shapes. So here's a nice shape. So what I'm doing is, these are called polar curves. I give the radius r as a function of theta. So there's r equals 2 cosine theta, and there's r equals 2 sine 2 theta. And so what you do is, for each value of theta, you calculate what is r. And so we can try to figure out, what is what. So does anybody remember what sine of 2 theta is? So what's the trig identity for sine of 2 theta? No. So sine of 2 theta is 2 sine theta cosine theta. We have to remember the angle addition formulas. So this is the same as 4 sine theta cosine theta. And in polar, x is r cosine theta, y is r sine theta, r squared is x squared plus y squared, and then theta is arctangent of y over x. So here's theta, here's y, here's x, here's r. This is how I go back and forth between polar and Cartesian coordinates. So if I give you your r equals 2 cosine theta, this is the same as r squared is 2r cosine theta. But what is r cosine theta equal? X. So this is the same as r squared, which is just x squared plus y squared equals 2x. So this is the same as x squared minus 2x plus y squared equals 0. Complete the square, x squared minus 2x plus 1 plus y squared equals 0. That's x minus 1 squared plus y minus 0 squared equals 1. This is a circle, center, 1, 0. And that's the blue curve. So r equals 2 cosine theta is just a nice way of writing the equation of the circle. And if I start off with theta equals 0, 2 cosine of 0 is 2. So that's going to start off over here. This would be the point, theta equals 0. And then for each value of theta, I keep seeing where do I go. And when I get to theta equals we want to be careful as to exactly what range we're looking at these at. Okay. Now the next one, 4 sine theta cosine theta equals r. I would multiply both sides by r, and I would get, 4r by r squared. I get 4 sine theta r cosine theta is r cubed, and I would get this strange curve involving x's and y's. And it turns out it's much easier for a lot of these to plot them if I can write them in polar form. So we're not going to do too much with this, but this is one of the topics, and it's just worth at least having one lecture on it, and just seeing that for certain shapes, it's easier to write them down as r as a function of theta than to write them down as something in terms of x and y. So as an exercise, try to figure out what this would look like. So not surprisingly, Mathematica has commands that allows you to do all these plots. So without too much trouble, we can do any of these plots. And so for instance, this is polar plot 2 cosine t, t goes from 0 to 2 pi. This is exactly what we had a moment ago. And then here's the polar plot 2 sine 2t, which we were talking about a moment ago. Let's actually switch to the screen and do mathematics for a moment. So here is the polar plot we just did a moment ago. Now what I'm going to do, manipulate. I'm going to do 2c goes from 0 to 1. All right, so so here we can see what happens as we draw it further and further. And so we really only need to get up to pi before we come all the way back to where we started. And so by doing it like this, we can see the path as it's going forward and forward. If we look at the next one, this is the polar plot I equals 2 sine 2t. We can get the 4 different leaves. And so what I can do I'll do the same thing as before. So you can see it being slowly added. I'll have c goes from 0 to 1. 0, 0, 1, to 1. And so what you can do is you can see as I increase the angle, how it traces out the object and which order it traces things out. And there's the nice curve as it goes through. Okay. So again, this is the 21st century. You want to be able to use tools like this to get a feel for what's going on. And you could make tables, which is what they would have done when I was a kid, but now you want to learn just how to program the computer to generate and give you a sense. Okay. So here is the cardioid. What kind of shape does this look like? Or maybe if you rotate it 90 degrees, what would this look like? A heart. So if you actually have to mathematically draw a heart, I strongly recommend the cardioid, 1 plus cosine t. And then you could ask, well, what if I played some games? What if I put a constant in front of the cosine t, and gave myself some freedom in terms of adjusting things? Can I make some more interesting shapes? And so, with a little bit of work, I found some stuff online about it. The equation is I equals a plus or minus, a times 1 plus or minus cosine theta. So we're just doing the case a equals 1. So it's the curve x squared plus y squared plus x squared equals x squared plus y squared. And so when you look at this in terms of a polynomial in terms of x and y, it's not so easy to see what's going on. When you write it in terms of r and theta, it's much easier. Why am I using t rather than theta as my variable? Normally we use r and theta for polar coordinates. Why am I using t? It's two reasons. So one is, theta is a Greek letter. And it's much easier for me to write t than to just spell out the word theta or to use the special symbol theta coming down. But also, what's the first letter of theta? T. So I'll use t for theta. Or you can even do t for time. It's not a bad choice. But you always want to think, why am I choosing the notation I'm choosing? Okay. So here's another famous one, the limit system. And its equation is r squared is a squared cosine 2 theta. Or r is a square root of cosine 2 theta. And so if you go through and you play the games, and you want to try to write it down algebraically in terms of x and y, you get x squared plus y squared squared is 2a squared, x squared minus y squared. So it's somewhat similar to what we had before, but a little bit different. If you have an object like this, the natural questions are, what is the perimeter? What is the area? We've seen already that perimeter is often a very difficult quantity to evaluate. Why is perimeter so difficult? What makes perimeter such a pain? What kind of integrals do you have to deal with? Square roots. We hate dealing with square roots. When we're doing volumes, we often have the radius squared. We're doing disks. And what's the volume of each infinitesimal disk? It's pi r squared times the thickness. Ah, good. Squaring things. I'll expand out. I'll use Henry David Thoreau. And so the bottom there's a beautiful formula. The area, and this is actually true for any polar region, is 1/2 the integral of r squared d theta. And so for the Leibniz, we know that r squared, at least when a equals 1, I guess we're just doing general and they can pull out the a, is just cosine 2 theta. And so we just have to integrate cosine 2 theta. Okay, well, that's not so bad. What function has derivative of cosine? The derivative of sine is cosine. So this would be 1/2 sine 2 theta. And then when we just evaluate it at pi fourths and minus pi over fourths, it will just become a squared. So if this formula is true, we can actually evaluate things very easily. When you hear area, what units are you thinking of? Meters squared. So whatever I'm integrating has to be a meters squared. So one way to do this is to learn something called multivariable calculus. And I could integrate over x and y. And then if I integrate dx dy, well, dx will be in what units? So dx would be what units? Meters. And dy would be what units? And so dx dy would be meters squared. So I could try to integrate this in polar. Now, what would be the units for the radius? Meters. So dr would be meters. What about the angle? What are the units for the angle? Radians. Radians is unitless. So what would d theta be? Unitless. What do you have to multiply the angle by to get a length? Well, if you multiply by 180 over pi, it's still unitless. You're just converting from radians to degrees. It's still unitless. If I give you an angle, there's a natural thing to multiply the angle by to get a length. And this is why we use radians. You multiply by something with a circle that sounds a lot like radians. The radius, right? Ever wonder why we call the thing radians? So if you have a circle of radius r.
Oh, and then is that the length of the curve?
Yes. Why radians? So if I give you a circle We'll call this a circle to be generous. Oh. So here's a circle. Here's my radius r. Here's an angle theta. Bless you, what is the length of this arc? Well, what's the perimeter of the entire circle? 2 pi r. What fraction of the perimeter do I have? Theta over 2 pi times 2 pi r is theta r. So the arc that makes an angle of theta with the center of the circle, its length is just theta times r. If r equals 1, then the measure of the arc is the same as the measure of the angle. They're different units. A lot of us might have the same numerical value in our bank accounts as Elon Musk, but his units might be in the billions, and our units might be in the dollars. The units matter. So I'm not saying 1 radian is the same as 1 meter. I'm saying the numerical value of how many radians is the same as the numerical value of how many meters is it. And so this is a great way to pass from an angular measurement to a distance. So d theta is unitless. R d theta would be meters. But I want meters squared. So what would be meters squared? How would I get meters squared using r's and d thetas? So what can I do to get from r d theta to meters squared? I could square, but then you would have a d theta squared. We never want to have the same infinitesimal twice. So how can I get from r d theta to an area? We've already got something in meters. What should I multiply it by to get it into meters squared? Okay, so how do I multiply by meters? What do I multiply it by? So one possibility is r squared d theta is in meters squared, which is an area. I could also do r d theta dr, which would also be meters squared. And we often write this as r dr d theta. I understand why we write it as r dr d theta. We put the r's together, but it's actually confusing to do so. It's much better to write it as r d theta because it's the r d theta that has length. The d theta by itself does not have, a meters does not have something like that. So these are natural ways that we can try to get areas by using polar coordinates. I could have something like an r squared d theta, or I could have an r dr d theta, which looks like the approach that multivariable calculus. We have 2 possibilities. Which possibility looks like the multivariable calculus approach? The r d theta dr. That gives me 2 variables to be integrating over. And so that would be the approach of multivariable calculus. The r squared d theta, I only have 1 variable that I'm integrating over. That's the Calc 2 approach. And this is similar to how we found the volumes of surfaces of revolution. It's technically, yes, it's a 3-dimensional problem. We're not allowed to do 3-dimensional integrals in this class, so we have to somehow convert it to a 1-dimensional problem. So we have tremendous symmetry. So we have all of these cylinders. We know the volume of each cylinder. Let's stack them together. So if you look at what's going on here, we have the 1/2 r squared d theta. Okay, can you think of anything where geometrically I might have a 1/2 of an area coming into play?
triangle.
Triangle. So looking at it as 1/2 r squared d theta, maybe 1/2 r squared d theta is 1/2 r times r d theta is maybe this is related to a triangle. So before we even try to prove the theorem, we have some idea of where it's coming from. Rather than trying to do things the way we did with integrating, y equals f of x, what shapes did we use for that? When we did our Riemann sums, what did we use? We used rectangles. Now we're going to use triangles. And that's where the 1/2 r d r d theta comes from. So again, this is the power of looking at a formula and asking, what does this look like? Is there any reason to expect this? And I'm writing 1/2 r squared d theta is 1/2 times r times r d theta. Okay. So basically here is the proof. So suppose, I just pulled this online. It's a much better picture than I will be able to draw. That looks really like a circle. So we have some curve, r equals theta. And then if I let theta change by a very small amount, the length of that change is going to just be r d theta. And that's going to be essentially like my base. My height is essentially going to be the radius. And so the area should essentially just be 1/2 of that. We've got to be a little bit careful because we want to make sure things are right angles and whatnot. But hopefully this gives you enough of a feel of where this formula is coming from. You can see the triangles coming in. Here's my curve. R is some function of theta, and these really do look like nice right triangles. Okay. Any questions on this? The other thing is, there's really not going to be that much of a change in R as I go from over here to over here, or if I come straight down. It's going to all be the initial radius plus a small change. So if I'm trying to think of how things change, it's going to be r plus a really small lower order term. And then when I multiply by the r d theta, the way you have to think about it is if you have the product of two small things, it's negligible. So if you think back to how we proved the fundamental theorem of calculus, we show that the upper sums and the lower sums converge to a common value. The problem is we broke things up into n pieces. So we had n sums. So if I tell you you're off by $1, is that a lot to be off by? No. But if I tell you we do this a quadrillion times, oh my. If I'm off by $1 and I do this a quadrillion times, if all of the errors are in the same direction, I'm now off by a quadrillion dollars, which is more money than is in the entire planet. So a very small error can magnify. So when we proved that the upper and the lower sums converged to a common value, it wasn't enough to show that each individual piece was close, because we had n pieces. So if the error was of size 1 over n, since we had n of them, n times 1 over n is of size 1. What we did is we showed each difference between an upper and a lower sum was of size 1 over n squared. If it's of size 1 over n squared, then even if I have n of them, it's still only going to be of size 1 over n. It's going to be negligible. That's what we can do here. This picture is not to scale. The theta is supposed to be infinitesimal. So for that infinitesimal, you're just going along the boundary of a very small circle. So you can say that, yes, the base really is just r d theta. It doesn't look like that in this picture. In this picture, it looks like, hey, there's a noticeable difference between the radius on the bottom and the radius up here. Yes, but in infinitesimal, the change is going to be so small that when I multiply it by the infinitesimal base, it's going to give me an infinitesimal squared. And that's not going to matter. So this is how you do polar integration. So the area would just be 1/2 the integral of r squared d theta. And it all comes down to can we actually calculate out this area? Can we do this integration? If we are lucky, we have functions that are nice. So one of them I think was the cardioid. So this was r equals a 1 plus cosine theta. So let's try the cardioid. So it was r equals 1 plus cosine theta. I think we had 0 less than equal to theta less than equal to pi. Quickly double check. Go back to Mathematica. Now do full plot. Oh, that's half the cardioid. Oh, sorry. It was the other figure that I was doing. It was the sine 2 theta, I think. Okay. So here I actually have to go all the way to 2 pi. And so if I do this, this is only half the cardioid. Or is it enough to just do half the cardioid? It's symmetrical, and so I could just multiply by 2. So maybe I'll do that. So here's my picture. Here we go. Here's our picture. So we need to double. Then double by symmetry. Okay, so you want to integrate, multiply by 2. Theta goes from 0 to pi. And then it's going to be 1/2 r of theta squared d theta. Okay, the 2's and the 1/2's cancel nicely. Good. What's r of theta? So what is r of theta for this problem? So it's written on this slide. It's 1 plus cosine theta. So this is r of theta is 1 plus cosine theta. And so here is r is 1 plus cosine theta. And so how would I integrate 1 plus cosine theta? So I've got 1 plus cosine theta squared d theta. Right, so what would the u substitution be? Okay, and then what would du be? And so you would have a sign coming in, we don't have a sign. So it's not a bad idea to try u substitution. What trig identity? There is a trig identity. So cosine of 2 theta is cosine squared theta minus sine squared theta. So this is the same as cosine squared theta minus 1 minus cosine squared theta. So this is 2 cosine squared theta minus 1. So cosine 2 theta plus 1 equals 2 cosine squared theta. So there's 2 ways to try to do this. I have 1 plus cosine theta. I could take theta here to just be theta over 2, and then I get 1 plus cosine theta is 2 cosine theta halves squared. Or I could expand the square and then use this. So this would be the same as the integral from 0 to pi of 1 plus 2 cosine theta plus cosine squared of theta d theta. Some of these integrals are actually pretty easy. What's the integral of 1 from 0 to pi?
Here. Oh, no, it's that, theta.
It's theta, and then we evaluated 0 and pi. So this would be theta at 0 and pi. What about 2 cosine theta? What function has derivative of cosine theta? Sine. This is going to be plus 2 sine theta at 0 and pi, plus the integral from 0 to pi of cosine squared of theta d theta. And so this one is just going to be pi. The next one is going to be 0. And we have the integral from 0 to pi of cosine squared of theta d theta. So for us,
to vie for the seat of MP in Madare constituency.
oops, there's something going on in the background. People in Zoom, could you please mute yourself? Thank you. Our integral is just going to be pi plus the integral from 0 to pi of cosine squared of theta d theta. This is just going to be pi plus the integral from 0 to pi, and now cosine squared is just going to be 1/2 plus 1/2 cosine 2 theta.
There's a problem. There's a problem when you see a man with hair like
And
this.
so given that we now have 1/2 plus 1/2 cosine theta, okay. So now we just have 2 integrals left to do. So the first one, what function has derivative 1/2?
Theta over 2.
Theta over 2. So this will become 1/2 theta at 0 and pi plus what function has derivative 1/2 cosine 2 theta? Well, the derivative of sine is cosine. But when I take the derivative of sine 2 theta, I'm going to get a 2. So it should be 1/4 sine of 2 theta at 0 and pi. And so this is just going to become 3/2 pi because this is the second one is 0. And so this is a way to finish up the integration. Some of these I could have actually done a little bit faster by noting that, if I integrate cosine 2 theta from 0 to pi, that's basically very similar to integrating cosine theta from 0 to 2 pi. I'm going through a full cycle. And what do you get if you integrate cosine over the full cycle? What should you get?
Circle.
Well, no, but what's the area under cosine if you go from the full cycle from 0 to 2 pi? 0. The positives cancel the negatives. And if you looked at what you had on the previous page, if I'm integrating cosine of theta from 0 to pi, I've got one of the positive regimes of cosine followed by one of the negative regimes. They perfectly cancel, and I would get 0. So we solved the problem, but we had to remember a little bit of trick. But by remembering that trick, we were able to get the area of the cardioid. The final answer involves pi. Is that surprising? No, this is involving trigs and stuff like that. I'm not surprised that there's something like that. There is another way to do this problem. So we had to integrate cosine squared from 0 to pi. Do you agree that this is the same as 1/2 the integral from 0 to 2 pi of cosine squared of theta d theta? Well, the integral of cosine squared from 0 to 2 pi is the same as the integral of sine squared from 0 to 2 pi, because sine and cosine just differ from each other by shifting by 90 degrees. So if I integrate one over full cycle, it's the same as integrating the other. So this is 1/2 the integral from 0 to 2 pi of cosine squared theta plus sine squared of theta over 2 d theta. Now it should be clear why I did this. What's the next line of simplification? What do I do next?
Take the 1/2 out.
Okay, let me see. Did I make a mistake on the previous slide? No. So what do I do next? I could take the 1/2 out. So this would be 1/4 the integral from 0 to 2 pi cosine squared theta plus sine squared of theta d theta. Now what do I do?
There's something involving cosine. Oh, you can split those.
Okay.
But does it involve a cosine squared plus sine squared equals 1?
Well, if cosine squared plus sine squared is 1, which would you rather integrate, 1 or cosine squared and sine squared? Remember, this is what we just had to do. We had to prove these trig identities to integrate cosine squared. I would much rather integrate 1. So this is exploiting symmetry. So by exploiting symmetry, this is the same as 1/4 the integral from 0 to 2 pi of 1 d theta. All right, that's 1/4 theta at 0 to 2 pi. So this is just 2 pi over 4 or pi halves. And notice pi halves is exactly what we got for this piece over here. This piece over here was pi halves. So without resorting to all those trig identities, we can still get the answer. And the reason is there are certain functions which are hard to integrate. Sometimes they have antiderivatives that are just painful. Sometimes, however, they have nice answers if you do the entire range, if you integrate over the entire range. If you integrate over a restricted range and you have to use the antiderivative, it's very nice. But if you integrate over a nice range, 0 to infinity, 0 to pi, something like that, often all the bad stuff cancels out and washes away. And you're left with just something that's very nice. So there's a couple of ways of doing problems like this. And so, if I have 1 minute left, so if I just switch back to Mathematica, integrate squared. So it actually gets the answer without too much trouble. This isn't so bad. But more involved ones could come up with a very painful antiderivative. But if you're at very nice places, a lot of times the bad terms will cancel away and you'll be left with a nice answer. So there's a lot of integrals that are painful in general, but are nice over specific regions. For this one, we really exploited symmetry. And that's the key idea to end with, is that this was all due to symmetry. We win because of symmetry. All right, so this is a good place to stop. So, as an application today, we saw how we could try to build orbits of planets from simple things. The Taylor series just adding more and more terms. We saw that we could, write down certain curves more nicely in polar than in Cartesian. We saw a little bit of an introduction to multivariable calculus, and we saw yet again that we can bypass all of that in Calc 2 by cleverly choosing how to do the integration. All right, have a good rest of the day.